assignment. I know Conroy, but I see you there. You were saying that you had some insight. Did you find a solution for that last question?
No, sir, I couldn't figure it out.
Couldn't figure it out. Oh,
As in, I couldn't figure out why the direction mattered.
okay. All right. Let me see. I will. Let me see if I can bring up the file. Network theorems. We're looking at the last. Okay. All right, so this is the question. And okay. So what I had indicated to you, is everyone seen the screen?
Yes, sir.
Yes, sir.
Okay. All right. What I was saying to you is that the currents, you're asked to find I, Y, R, and B, right? So what I was recommending to you is that you would have two loops. This is one loop. This is one. Two meshes rather. So you can make that I1 and make that I2.
Sir, that was the approach I took.
And that would be perfectly correct. All right, and then you write the two loop equations for these two. So for loop one, this will be the voltage. I mean, I understand that the double-ended arrow may be a bit misleading, but whichever you choose, let us take this. Let us take the voltage to be that, and down here the voltage to be that. All right. So we are saying that the potential here is higher. So I'm putting the plus just for the purpose of saying higher potential, okay? So this is higher relative to that, and similarly here, that to that, okay? So if you were to do that, then what you would have is that for loop or mesh one, it would be I1, or then again, we're all experts now, right? So for mesh one, if we were to write the matrix, for mesh one, it would be 6 plus J8 minus 3 minus J4. And then we have minus 3 minus J4 and 6 plus J8. All right. And then we'd have I1 and I2. For the upper one, it would be 415 at angle 120. Oops, 120. And down here, it would be at angle 0. Fair enough? And so we can find I1 and I2. And from that, we can find our currents.
Sir.
Yes, sir.
Okay, so that's what I have. But what I did first was, you see the source? I had the arrow going, for the second source at the bottom, I had the arrow going the other way.
Oh, okay.
Yeah, and it didn't work.
As I said, then that would have, I'm now seeing that would have made it misleading. All right. So you'd have that and that. Okay.
Yeah. Yes, sir.
All right. All right. For the other questions, what you can do is I will be opening up the solutions are all on Schoology. All right. There's a folder there that has tests and exams. I believe that's the name of it. I believe that's the name. I have it there. Let me just double check. Exam papers and solutions. All right. So I will publish that. And the solutions to the questions I gave you are all there. So all the questions that I gave you during week 1, you can access them using going into that folder. All right. So we'll continue where we left off on Monday. We're looking on, oh Lord, we're looking at 2-port networks. All right. And today we want to look at these parameters. We want to look at 2 parameters. We want to look at the admittance and the impedance parameters, and just see, based on what we have been saying since Monday, see how we use these parameters in circuit analysis. We look at a simple circuit and see how we go about developing or finding these parameters. But thereafter, we'll just look at how we use them. For the most part, in your areas of specialization, you will find that you will get these parameters. So you'll have these parameters. The question is, how to use them. That would be your challenge. So today, as I said before, we're going to be focusing on the impedance and the admittance parameters. So let's get started. Not sure what I got there. All right. So, as we indicated on Monday, we can describe the operation of a circuit using what we refer to as circuit parameters. All right. These circuit parameters will help us to fully define the operation of the circuit. And then what we will be looking at is what then happens when I change the load or the input to these circuits. Okay. And we're going to start by talking about the admittance parameters. And the admittance parameters, the key here is that the input and output currents, that's a key phrase, the input and output currents of your 2-port network can be determined from a set of equations. So what's the focus when we're using admittance? The input and output currents. And the equations, I1, and we introduce some terms now. We call Y11 V1 plus Y12 V2. And for the output current I2, we have Y21 V1 plus Y22 V2. And from a diagrammatical standpoint, yes, that is what we have. Remember the convention that the upper terminal is more positive or is at a higher potential than the lower, and that the currents are entering the upper terminals. Right. So the I1 that we're referring to, it's that I1, I2, and then of course the V1, okay, that would be the voltage at that point, and then V2, okay, would be that V2. Okay. Now, as we said here, the parameters can be formed, or the equations can be formed using, okay, I'm not sure what is happening here. Let me just. All right. Okay. So the voltages V1 and V2 are made zero by short circuiting the respective ports. Yes. So if I put that short circuit across port 1,
Anything on my screen, sir?
you're not seeing anything.
No, sir.
Let us try and correct this. I don't know what is happening today. All right. All right, let me correct that and get back to you. Let's go again. Are you seeing it now?
Yes, sir.
All right. Sorry about that. Okay. So voltages V1 and V2, we can make them zero by short circuiting the respective ports. So if I short circuit port 1, it will make the voltage zero. Obviously, short circuiting the point will not impact the current. We'll still have a current, just that the voltage at that point will be zero. Now, if I look at equation 1, if I make V2 zero, right? Remember we said that we are using the superposition theorem. That's what we said just now. And we remember what superposition theorem states, yes? So if I use superposition, I would have to make one source zero, and then you see what happens with the other one, you know? Good. So if I make V2 zero, then from the equation, I am left with this because V2 is zero. So I1 would be equal to Y11 times V1, which means that Y11 would be equal to I1 over V1. Okay? And we can do the same for the other parameters. Now, let us just note that that Y11, we know that Y11, or should I say Y, is an admittance. And we know that admittance, Y, is equal to the reciprocal of impedance. Yes? And of course, impedance is equal to V over I. So Y, I know you all knew this already. Y is equal to I over V. All right? So before we get into, any further details with this, what I'm going to do is just to look at the other parameters. So we have Y11. Let's see for Y12. Y12 would be equal to I1 over V2 if I make V1 zero. Again, going back to the equation. All right, these are the equations. So if I make V2 zero, then that would be eliminated. So I can find Y11 from that expression. If I made V1 zero, then that goes, and I'd get Y12 from that expression. So I'd get Y12 being equal to I1 over V2. All right, and then we'll repeat the same for the second equation. So we have Y11, so I have Y12. I can also find Y21 and also Y22. Fair enough? Now, one of the things you would have noticed by now with networks too is that we make use of matrices. So if you don't like matrices, then, you know, you may want to spend a little time on, you know, or if you're weak on matrices, you may want to spend a little time and refresh yourself, because we're going to be using it quite a bit. So we have y11, we have y12, we have y21, and we have y22. And I can put all of these parameters in a single matrix. Yes? So in matrix form, and this is just rewriting the equations that we had before. Yes? So the top one would be equation 1. Yes? So that would be equation 1. And then, of course, the bottom one would be equation 2. So these parameters, the y11, 12, 21, and 22, we can put them all in matrices, or in a single matrix rather. All right? Everybody clear so far? Is there
Yes, sir.
anyone who is unsure what I'm talking about? All right, so having said that, I now need to try and give an explanation as to how we go about determining, you know, these parameters. So let's talk about these parameters for a little while. And, you know, if you're, maybe you would have noticed that there's a little pattern that has developed here. So first thing, the position of the matrix element indicates which ports are being compared. So let's go back now. Y11, the position in the matrix is 1, 1. 1, 1 represents input. Yes? In our case, the 1 is input and the 2 is the output. All right? So the 1 is the input, 2 is the output. So where I have 1, 1, and if we go back to what we said, y11 is equal to I1 over V1. So 1, 1 is telling us that we are comparing the current at the input and the voltage at the input. All right? So what we have here, firstly, we know it's Y. So if it is Y, it's an admittance. Y21 is telling us that we are looking at port 2 divided by port 1. So it's a quantity at port 2 divided by 1 at port 1. Because it's an admittance, we know it is a current divided by a voltage. So Y21 would be equal to I2 over V1. The other thing we need to note, ladies and gentlemen, the other thing we need to note is that in order for me to get Y21, I had to short circuit one of the ports, or rather, I had to make the other variable 0. In this case, the variable was the voltage, and the voltage I made 0 was at port 2. So Y21 is equal to I2 over V1, but that is true only if V2 is 0. So I can go further in defining this parameter by saying that Y21 is derived when port 2 is short-circuited. So the nomenclature, or the name used to describe the parameter, is dependent on what is done when deriving its value. All right? So let us summarize. Let us summarize everything that I just said with respect to this parameter, y21. Let us summarize that. And here's the summary. Y21 involves both input and output quantities. Means that it's transferred. So in other words, it's going across the network. So the fact that I am combining input and output, the term transfer comes into place or comes into play. So the final name for Y21, yes, the complete name for that parameter is the short circuit, because remember I had to short circuit a port in order to get it. Transfer, because it involves both input and output quantities. And admittance, because it is current over voltage. So again, one, we know that we had to short circuit a port in order to get it. So the first part of the name, the short circuit. Secondly, it involved both input and output quantities. So we refer to it as transfer. And then thirdly, it is current over voltage. And so we refer to it as an admittance, or we know it's an admittance. So Y21 is the short circuit transfer admittance. Any questions? Any questions? Okay. All right. So if there are no questions, let us look at the other three parameters. All right. Let's see who we have on board. So Brown. Where's for Brown? Give me the name for Y11. Give me the full name for Y11. So Brown?
Admittance row
Come on,
one.
Mr. Brown, Mr. Brown, Brown, where is he? You're not hearing me, sir? Where's for Brown? Mr. Brown not here. Okay. All right, so he's not here. Okay. Jerry Morrison. Morrison. Oh.
Yes, sir. Yes, sir.
Yeah, man, go ahead.
Sir, I just joined the work just now because I was rushing home from work.
You just joined.
Yes, sir.
Eh? Well, that's not according to my information before me, Mr.
A few
Morrison.
minutes.
But anyway, well, just is a very strong word, Mr. Morrison. Anyway.
Hello.
So McFarlane.
Yes, sir.
Yeah. Take a shot at Y11.
All right, sir. So port 2 is short circuiting.
Mm-hmm.
So V2 equals 0. And then
I just want the name. Just give me the name.
the name.
Yeah, man. Give me the name for Y11. I gave you the name for Y21. I want you to give me the complete name for Y11. Yes, Mr. Mark. So, go ahead, man. Just take a shot at it.
I don't even know what to say to take a shot.
Sir, can I try?
Sure, go ahead.
The short circuit admittance.
All right. Good attempt. Very good attempt. Good attempt.
Sir,
But look at the name I have for Y21. Look at the complete name I have for Y21. What have you missed out?
all right, sir. The short circuit non-transfer admittance.
All right, you're thinking. But what is it that we are dividing to get Y11? What would we be dividing?
Sir, current by voltage.
Okay, but which current?
I1 and V1.
And what does I1 represent?
Input current.
Input current. And what does V1 represent?
Input voltage.
Absolutely. So if you are dividing the input current by the input voltage, what do you think the name would be?
Oh, short circuit impedance.
Input current over input voltage.
What, input admittance?
Huh?
Input admittance?
So give me the full name. What's the full name? What's the
Short
complete
circuit
name?
input in admittance.
Who is that?
Adams.
Adams. Okay. Give me the complete name again.
The short circuit input admittance.
Absolutely. All right. So Y11, it's an admittance. It's developed by short circuiting a port. Yes. And therefore, and it's the input current over the input voltage. So it is the short circuit input admittance. All right. So how about Y12?
Short circuit output admittance.
No, 1, 2.
Short circuit transfer admittance.
Absolutely. It will be the same as 2, 1 because it's looking at output and input. And then finally, Y22.
Short circuit output admittance.
You see how easy it is?
Yes,
All
sir.
right.
Yes, sir.
Good. All right. So those would be the names for the parameters. So just by virtue of even the names, you would know exactly how to find them. And that is going to become important later on in this particular topic. All right. So now that we know the equations that we would use to get these parameters, all right. Now that we know the equations, what I want to do is just to go through a simple exercise in terms of how we go about determining the parameters. All right. So here goes. So take this down for me, please. So we want to derive the parameters, the admittance parameters for this network. There are 3 resistors. We know the convention. So prior to now, what I was giving you is just a black box. You didn't know what was inside that box, but we were just showing you that currents were going in at the upper terminals, and we had V1 and V2. Okay? So now I'm opening up the box, and what we want to do is to find the parameters and use them to define this network. All right? So let's start with first thing. These are admittance parameters. And in order to find the 4 admittance parameters, what do we know we have to do to the ports?
So you have to short one at a
All right?
time.
So we have to short circuit the ports. Okay, good. So the first thing I want to do, we want to short circuit port 2. Now, if I short circuit port 2, the information I have V1, okay? I still have I1, and of course, I would have I2. Would I agree with that? So the fact that I still have these, because in short circuiting port 2, you will agree that V2 is now 0.
Yes, sir.
Good. So let us look at the parameters. V1 over I1, and based on the fact that I have the port 2 short circuited, it means that no current will be flowing through this resistor. Fair enough? So whatever current is going through the 10 ohm resistor is the same current that will flow through the short circuited port. Everybody agree with that?
Yes, sir.
Yes, sir.
Yes, sir.
So V1 over I1, which is just the impedance looking into the terminals, will be 5 in parallel with 10. 5 in parallel with 10, yes, product over sum gives us 10 over 3. Of course, that will be ohms. But what we are interested in is I1 over V1. So it's just a reciprocal of that. All right. Which means, therefore, that I1 over V1, which is Y11, is equal to 0.3 Siemens. So Y11 is 0.3. Everybody comfortable with that?
Yes, sir.
Now, if I go again?
I was saying so far, sir.
Oh, okay. Now,
Sir,
yes.
sir, can you go over why is it that we did the reciprocal?
Because I want the admittance. It's the admittance that we're finding.
Oh, okay, got you.
All right, and the V over I would give us the impedance, but it's admittance we want, so we find the reciprocal.
Okay.
All right, cool. Now, if I maintain the short circuit, as I said before, what we would still have available to us would be I2. I'd still have I2. Yes, I1 and V1. So it means, therefore, that the only other admittance I could find would be Y12. But I agree with that?
Yes, sir.
No, man, you can't agree with that because it's wrong. I want you guys to be thinking, I don't want you just to agree because I say so. It's an admittance, so it's current over voltage. Only 2 currents we have. Yes? So it's I2 over V1, which would give us Y21. Not 1, 2.
Okay.
Sorry, I had to do it. All right.
That's fine, sir. Best
So-
way to learn, huh?
So we have here I2. Now, which resistor would I2 be flowing through?
The 10, sir.
Then
The 10 ohm. Excellent. All right. So if it's flowing through the 10 ohm, all I need to do is to find the relationship between V1, the 10 ohm, and I2. Yes? Now, based on the circuit, with this short circuit in place, yes, what would be the current flowing through the 10 ohm resistor as a result of V1?
So I just, V1
Huh?
over the 10. V1 over the 10 ohm.
V1 over 10, because the 5 and the 10 are in parallel.
Parallel, yes.
Okay? Now, next thing. In what direction would the current be flowing?
Sir, from left to right, sir.
From left to right, because as we said before, this terminal is at a higher potential. Agreed? So it means that the current will be going in that direction. But in which direction is I2 flowing?
Towards the higher potential.
All right, so it means that this parameter, so it means that this parameter would be negative. So that is what we just went through. So with the port still short-circuited, yes, we can find a relationship between V1 and I2. And V1 would be equal to minus 10 I2 because I2 would be going in the opposite direction to which the actual current as a result of V1 would be flowing. All right, so I2 over V1, which is Y21, would be 1 over minus 10, or minus 1 over 10, it really doesn't matter, yes, which gives us minus 0.1 Siemens.
Excuse me, sir.
Yeah, man, go ahead.
Mr. Brown is asking for you to let him in back. He said that he stepped away from his computer.
Okay. But I don't have a waiting room.
why current flow from left to right, sir?
I am not blocking him, you know, Mr. Henry.
Okay, sir, I'll notify him.
I'm not blocking anybody. All right, so let us go back to the network. Let's go back to the network. All right, and this time around, let me go back to the original network since it doesn't have a short circuit. This time around, I want to short circuit port 1. Now, which parameters would I be able to determine? I have V2, I have I2, and I have I1. Yes?
Sir, you can get Y12, sir.
So I can get Y12, which would be equal to? So Y12 would be equal to?
I1 over V.
Y1 over V2.
Okay. Which other?
Y22.
Y22, which would be I2
Over
over V2. All right. Excellent. All right. Now, for Y22, I'm now looking in that direction, right? For Y22, we can find V2 over I2, which is Z2, yes? What would that, well, call it Z22. What would that be equal to? What's the impedance seeing looking in this direction?
20 parallel with 10.
Parallel with 10.
10.
That's 20 in parallel with 10.
Okay.
All right. So we have 200
Divided by 3.
over 30. All right.
6.667.
No, we're going to leave it at that. We're going to leave it at that.
Get most relevant fraction, you know, so yeah, you shouldn't even bother say that.
Which means that y22 is going to be equal to
30 over.
the reciprocal, which is 3
over 20.
over 20. All right? And that would give us 0.15 Siemens. Fair enough? Now, how about y12?
1, 2.
Which
Oh,
resistor would I1 be flowing through?
Go through the 20 and the 10 in series.
Which resistor would I1 be flowing through?
Combination.
The 10
10 ohm.
10 ohm resistor.
Only the 10 ohm resistor. All right. So I1 will be flowing through the 10. Now, what is the relationship between I1, the 10 ohm resistor, and V2?
V2 equal to negative 10 I1.
Which means that Y12 would be equal to
1 over negative 10.
which gives us minus 0.1 Siemens.
Sir, so you can go over that from again, please, sir.
Which one?
The last one. When the current I1 knows.
I1 would be the current passing through the 10 ohm.
So,
Because no current to go through this, because this is short circuited.
okay.
No current to go through the 5 ohm, so I1 would pass through 10.
Yeah.
All
But
right?
then but it's like I1 to be the same current going through the 20 as well.
You tell me.
So yes, but I said that, sir.
It can't be, it cannot be, Mr. Wilson. Anyway. I1, the only resistor that you have I1 going through, I1 by I1 as we know it, good, is through the 10 ohm. As we know it, there's a combination of I1 and 2 that is going through the 20.
Okay.
There's a reason why networks 1 is a prerequisite, Anyway.
Sir, just a quick question.
Yeah, man. Go ahead.
Looking at the values here, correct, sir? Would it be safe to say that this is just like writing the matrix would be just like the previous matrix where the 2, 1 and the 1, 2 would be the same?
Which previous matrix we're talking about?
When we
Yes,
were
sir,
using, was it mesh?
No, don't go back there. Don't go back there. I don't want you to link them in any way. Just
Okay.
consider, just as far as that was concerned, it was just using matrices as a tool. All right. Here, here our focus is on something completely different. I don't want you to link the two. Don't link the two. All right. All right. So what I just went through with Y22 and Y12, here it is. All right. So you have Y12, which is minus 0.1, and you have Y22, which is 0.15 Siemens. So what I want to do here is just to put all these parameters together in matrix form. In matrix form, Finish with this?
Hold on, sir. 1 second.
All right, can we move on?
Yeah, man.
Okay. So in matrix form, we have I1, I2, yes. And note, when in matrix form, just let me, because there are some things we note, when I'm speaking about the individual parameters, note that I use a lowercase y. All right. However, when I'm dealing with the matrix, this is now uppercase y. All right. So this would be I is equal to uppercase y times v. All right. So here's our matrix. And what we want to now do is to, use it for something of value. So what I want us to do now is to, remember we said that once I describe my network using these parameters, I can use the parameters to determine what will happen on the input side if I change the load, or what will happen to the load if I change the input and all of that. So what we're going to do now is to use these parameters to analyze a simple network. All right, because this evening, it's just about introduction to two-port networks. All right. So take this question for me. Okay. So we're not, I mean, this is introduction, so there's no point in, creating too much of a difficulty. What we have here, students, is that all of this you would recognize. All of this section is the network that we just analyzed. All right. So what we need to be able to do is to use V1 or use what we have connected to the network and write them in terms of V1, I1, I2, and V2. And then put that into our matrix equation and solve. So looking at what we have here, what would be the relationship between the 4 ohm resistor, V2, and I2? What would be the relationship between those three? Anybody?
V2 is
2 over I2
I2 times 4.
Go again.
V2 over the I2 would equal to 4.
Right.
So V2 let me put the 4 here, right? So V2 over 4 is equal to I2. All right? Okay, now I'll tell you up front that that is only correct to a point. Anybody can spot the reason why that is the case? Why is it only correct to a point?
Because of the 15 amp source?
No, man, it's only over this side we're dealing with.
Oh,
We're just looking at these three. That's all we're looking at. We're looking on the output side. Why is this only correct to a point?
Because V2 can be short circuited.
No, man. We have, this is a circuit. This is a network that we're asked to analyze. I asked for the relationship between V2, I2, and the 4 ohm. Excuse me.
Sir, sir, can I say? Sir, you hear me?
Go ahead, man.
All right. Based on observation, VI1 is traveling.
No. Leave I1 out of it. You're only looking at those three. All you're looking at is I2, V2, and I4.
Sorry, I2. I2 is traveling from right to left, so I'm just figuring that I2 probably be negative.
You're absolutely right. Because, this is when we went through those preliminary stuff on Monday, when we talked about the convention, what did we say about this upper terminal? I see I even put it in, which wouldn't be in a typical network, but I have shown it here. I've said that that this terminal, yes, this terminal is positive with respect to the bottom one. Isn't that what we said? So if the potential at this point is higher, then what direction would we expect the current to be going in?
Should be flowing towards it, sir.
So it will be going down. All right. So the current through the 4 ohm would be going from top to bottom. But the I2 is going from bottom to top based on convention. Therefore, what we would have to indicate here is that V2 over 4 is minus I2. Or we can say V2 is equal to minus 4 I2. Everybody with me? Is there anybody who is unclear about that? Just tell me if you're unclear.
Sir. Can you say that again?
Huh? I'm saying.
Can you say that again?
that based on what we have here, based on what we have over here, the potential here, V2 by convention, this is at a higher potential than that, by convention. That's what we started with. That's what we gave you on Monday. We're saying also that because it is at a higher potential, then the current through the 4 ohm, when I connect that 4 ohm resistor, the current through it would actually be going down. However, I2, which is the current through the 4 ohm, is actually going up. So it means that V2 over 4 will be the negative of I2. I cross multiply to get that. So that is on the output side. Now I come to the input side. So let's stick a pin with that for the time being. So I come now to the input side. On the input side, I have here the 15 amp source. I have the 10 ohm resistor. Yes. And I want to use these two in an expression that connects I1 and V1. All right, so all I'm using are these items here. Let me take out that big red one. All right, all I'm using are these 4. The 15 amp source, the 10 ohm resistor, V1 and I1. It has nothing to do with the rest with the circuit beyond that point. I just want an expression that connects all 4. So work with me now. What would be the relationship between I1 and V1 in terms of what we have here? Tell me the principles that you would consider applying.
I would say V1 is equal to 15 amp minus I1 times 10 ohm.
15. Go again. V1 equal
15 amps minus I1 in bracket times the 10 ohm.
All right. Now, let us explore why that has to be incorrect. Yes.
So is it because it's in convention thing?
Hold on, no man. We can explore why it is incorrect. I don't have a problem with being incorrect, because we learn from our mistakes. Colin Powell, no? All right. Now, what is V1? V1 is a voltage. All right? And you said V1 is equal to 15 minus something. What is the 15? What does that represent?
Current, sorry.
A current. Can you subtract a voltage from a current? No.
Yeah.
It's dimensionally impossible. All right?
Let me say.
There.
All right. So,
Sir,
I could deal with what was said, and then I come to the other option.
Sir, is it 15 minus V1 over 10 equal I1?
I asked, before we get into the answers, what I want you to do, ladies and gentlemen, is to be systematic in your approach. So the first thing I asked, don't give me an answer, a final answer. What I asked for was what principle you're going to apply.
Current divider.
You cannot apply current divider.
No, not divider. Kirchhoff. Current law.
Current law. And where are you going to apply that current law?
At the node of the 15 amp source and the 10 ohm.
Excellent. So you're going to apply the current law at that point. So what do you know? You know that 15 amperes is flowing into the node. Yes? What else do you know? You know that I1 is flowing away from the node. Yes? So it means that you need an expression for the current flowing through the 10. Everybody agree with that?
Yeah, yeah.
Yes, sir.
Yes,
So
sir.
I1 is going to be equal to 15 minus the current through the 10. And what is the current through the 10?
V1 over 10.
V1 over 10. So you see, folks, what I want you to do is think about the principle before you start throwing numbers at it. Right? And so you now have an expression linking all four.
Sir, but I same thing with it, sir, but I just that you have it in terms of I1. I said it to you in terms of V1, sir.
All right, if you want to convince yourself. But I am absolutely sure you said V1 is equal to 15 minus I1 times 10 in bracket.
And V1 is equal to the 15 amp minus I1. And that in bracket and then I times it by the 10 ohm, sir. But if I transpose it to get back this.
No. It's negative.
Okay, all right, cool. All right, so what do we have therefore? Remember the equation that we had here? How many unknowns do we have?
4, sir.
4. Now, for me to solve this equation, there are two equations. So I need a maximum of 2 variables, yes? Or 2 unknowns. So what we have done, we have written an equation, we have written an expression for I1, and we have written an expression for V2. That's all we have done. And the expressions that we just developed, so we have one for V2, we have one for I1. Yes? The expression we have developed. This is I1, which is 15 minus V1 over 10. Okay? And this is V2. So I now have an expression where there are only 2 unknowns. So go ahead for me, just to make sure we're comfortable. Go ahead for me and solve the equation. Of course, as is, you wouldn't be able to just, use matrices and solve it. But simplify it and find V1 and I2 for me. And just confirm that it's equal to that. And then, of course, you would find V2 and I1. So do that for me, please. Okay, so has anyone verified any of this? All right. Just state the results and verify them in your own time. All right. So we want to move on quickly to the next set of parameters that we have scheduled to look at this evening. So impedance parameters. Now, I went very slowly through the admittance parameters just to help you understand some of the basic principles. And for the most part, everything that we said about admittance parameters, we're just going to say the opposite for your impedance parameters. All right? So here goes. For the equations, what we are looking at are the input and output voltages. So for the admittance, we're looking at input and output currents. For your impedance, we are looking at the voltages. And these are written with respect to the input and output currents. Okay? So V2, Z21I1, Z22I2. And again, we use the superposition theorem. And it's the same network as we had before. All right, we have V1 and V2, we have I1 and I2. Again, the upper terminals being at a higher, assumed to be at the higher potential, and the currents going into the network at the upper terminals. So these are your equations for your impedance parameters. Now, as I said before, for the impedance parameters, we are just going to do the opposite of what we did for the admittance. So, whereas for the admittance, we would have short-circuited a port, for your impedance parameters, it will be open-circuited, because in order to make a current zero, then we need to open-circuit the path that would have allowed that current to flow. So, for the impedance parameters, yes, the currents are made zero by open circuiting the ports. So for equations 1 and 2, again, there are impedances. So if it's an impedance, it's what? Voltage over current. For admittance, it was current over voltage. So if we look at both equations and we apply superposition, then Z11 would be equal to V1 over I1, when of course I2 is made zero. Z21 would be V2 over Z1 over I1, sorry, with I2 being equal to zero. Z12, V1 over I2 with I1 zero. And Z22 would be V2 over I2 with I1 being equal to zero. Okay. And then we can look now at the nomenclature. All right. So first thing, what we did in getting these parameters is that we used an open circuit. The same principle applies in terms of input, transfer, and output. So if we go to the naming of the parameters, yes, Z11 is the open circuit input impedance. So let's include their input. So open circuit input impedance. Okay, what would Z21 be? What would the name given to that?
Open circuit transfer impedance.
Good. And Z12?
Same thing.
Same thing. And Z22?
Open circuit output impedance.
Excellent. All right. So let us see how we now go about determining these parameters. All right. As before, of course, we can write them as a matrix. Right? So we have V1, V2, Z11, Z121. Again, remember, the matrix is uppercase Z. Yes. So here we have V is equal to Z times I. All right. So let's go back to the network that we looked at earlier. And what we want to be doing is to deriving the impedance parameters. Right? So determine the impedance parameters for the network shown. Same network. All right. In this instance, however, what we want are the impedance parameters. And because we are looking at impedance parameters, we know that we're going to be dealing with open circuit values. All right. So with port 2 open, if port 2 is open, what we know is that if this is open, then I2 would be equal to 0. So what I am left with, or what you'll be left with, is I1, V1, and V2. And what we therefore need to find are the relationships between I1 and V1. So the relationship between I1 and V1 would give us Z11. The relationship between V2 and I1, all right, so the relationship between V2 and I1 would give us Z21. And then, of course, when we reverse and we look at this as this port as being open circuited, then what we'd be left with, yes, would be V1, I2, and V2, because I1 would now be 0. All right, so that's what we're after for these parameters. So let's jump into that. So with port 2 open circuited, if I open circuit port 2, then V1 over I1, which is the impedance looking into that port, will now be 5 in parallel with 10 in series with 20. So if I'm looking into this port, yes, it will be 5 in parallel with these two in series. Not too sure why I even went to the decimal, but Z11 is 150 over 35. Please don't include the decimal. I really don't know why I did that, but anyway. With the same, focusing on the same port, meaning port 2 remaining open, as we said just now, we can find Z21. So with that same port open, Z21 would be V2 over I1. Now, let me just go back to the circuit and show you the approach that I'm going to take. Right. So with this, if we look back at the circuit, remember what I'm interested in. I'm interested in finding the relationship between V2 and I1. So I want an expression for V2 in terms of I1. Now I1 would come to that node and it will divide between the 5 and 30. All right? So it will be dividing between the 5 ohm and the 30. And of course, the current that comes in this direction, if I call it Ix, yes, then Ix would flow through the 10, but it would also flow through the 20. If it flows through the 20, well, not if, flowing through the 20, the voltage drop across the 20. Yes? The voltage drop across the 20, which of course would have polarities plus minus. Yes? That voltage drop would be equal to V2. Does everyone agree with that? Or is there anybody who disagrees with that analysis or is unclear?
Sir, can you run that again, please?
I am interested in finding an expression for V2 in terms of I1. All right? So I1 comes to this node. It divides between the 5 and 30. You agree with that?
Yes, sir.
All right. So the current that goes in that direction, I'm going to call it Ix. So it's a component of I1 that goes there. So I can use current divider and write Ix in terms of I1. Yes? Ix would then flow through the 20 ohm. And because Ix is flowing through the 20 ohm, I'd be able to find the voltage drop across the 20 ohm, which would be equal to V2. So I then now have an expression in terms of I1 and V2, and then I extract the relationship V1, V2 over I1, which is Z21. Right? So that's the approach. So going back to what we were looking at. So Z21 is V2 over I1. So the equation, what I just explained to you in terms of the circuit, what we have done here, this would be the current division. So this current would be flowing through the 20 ohm. This would be our Ix. And 20 Ix would give you V2. So V2, you just take down the I1. So we have 100 over 35. Right, as I said, ignore that for the time. So Z11, 150 over 35. Z21 is 100 over 35. Okay? All right. I'm going to go to the next port. So I make port 1 open. So I open port 1. Now, if I open port 1, it means that I1 is 0, but I still have a voltage. So remember, an open circuit does not mean that you do not have a voltage present. All right? Okay, so if I open circuit port 1, then Z22, and that's the impedance looking into port 2 with port 1 open, would be 20 in parallel with 10 and 5 in series. So I get 300 over 35. And the same reasoning that I just did for Z21, I'm going to use it for Z12. So I'm going to find the voltage drop across the 5 ohm resistor in terms of I2. And if I do that, then we get 100 over 35. Again, just scratch this. All right? So I can write my matrix equation. So I have V1, V2 is equal to 1 over 35, 150, 100, 100, 300 times I1, I2. Any questions? Any questions? Crystal clear? Okay. All right. So, I didn't get that.
Yes, sir. Yes, sir.
All right, cool. So, you know, my next step is to go back to the same question we just did. All right, so we go back to that question. Take the question for me. Oh, well, you already have it. What you're now going to do is to use the matrix equation. So now you have V1, V2, yes? And as you would have noted, nothing has changed with the circuit. So it means that the expression we had for I1 would remain the same. The expression we had for V2 would remain the same. If you prefer, you may want to rearrange the equation. So what we had was that I1 was equal to 15 minus V1 over 10. Yes? You can now say well, V1 over 10 is equal to 15 minus I1. So V1 is equal to 10 to 15 I1. All right. So now you can substitute for V1. Totally up to you. Right. So everybody have the question? So go ahead and calculate for me the voltages and currents. That is V1, V2, I1, and I2. And while you do that, I will mark my register. Could the person who is listed here as Galaxy S10 indicate who they are, please? Who is Galaxy S10?
That would be me, sir. Jamal Kamika.
Who?
Jamal.
Yeah.
Yes.
Are you registered in school register?
Yes, sir. Earlier today.
Oh, okay. All right, good. All right, good. There are two Nick. There are two Nicks shown here.
Sir.
Can you identify yourselves?
Sir, Nicholas, I same person, sir, but I'm having some issue with my laptop audio, sir.
Okay.
Yes.
So this is Nick who? Watson?
Nicholas Lewis, sir.
Lewis, okay. Is Dre Morrison, Trevon Morrison?
Yes, sir.
Students, I'm going to ask you, next time you join the class, please have your full name there, as I will not go through this process again.
Okay, so I guess it. What do I change my name, sir? Because that's the name I get with Zoom.
You can't change. Okay. All right. Are we able to confirm any other values? All right, so we have so you can leave the V1 and the V2 if you so choose. You can leave V1 and V2 over here, and that's equal to 1/35. We had what? 150, 100, 100, and 300. Yes. And then you can make the substitutions for the I1 on this side. So you'd have 15 minus V1 over 10. Yes. And for this one, I2 would have been minus V2 over 4. Right? So you now have two equations in V1 and V2. You solve them, and all the things being equal, you will get the same result. And the point we're trying to make here is that it doesn't matter which set of parameters you use. Yes, you'll be able to tell what is happening to the network. So in one instance, and as I said, this is introduction. So in one instance, we use admittance parameters. We have used the impedance parameters. And once you have gone through this, and I am leaving it for you to complete, you will note that you'll get the same result. So to wrap up this, just a moment. All right, so to wrap up this evening's class, we just want to make some notations, some things that you need to take careful note of. All right, so Z11 is not equal to the reciprocal of Y11, nor is Z22 the reciprocal of Y22. And we can say the same for the impedances. If you recall, Y11, I believe, was 0.0 3, and y1, 2, and 2, 1 were minus 0.1, if my memory serves me right. Yes? And obviously, these are not equal to 100 over 35 or 35 over 100. Totally different. So the individual parameters cannot simply be inverted for you to find the corresponding impedance and admittance. However, the inverse or the reciprocal of the entire matrix will give you the corresponding matrix. So in other words, the impedance matrix can be found by finding the inverse of the admittance matrix and vice versa. All right? That is something that we need to know. So that's the final thing we're going to mention today. All right, and I'm asking you to just do the conversion, do the inversion for yourself. All right, invert the admittance matrix, and you'll get the impedance matrix. Invert the impedance matrix, and you'll get the admittance matrix. And I'm encouraging you just to spend some quality time going through what we have looked at this afternoon into this evening. And we'll pick it up from here with another set of parameters next time. And well, hopefully we'll be able to complete all the parameters in the next class. All right, and then we will have some fun thereafter. All right, so that's it for today. Have a good evening.
You too, sir.
Yes, sir.
Thank you, sir.
Take care.
Yes, sir.
Buenas noches.
Excuse me, sir. Are you still online?
Yeah, man, I'm still there.
I have a question. I registered for the module today, so I have missed the previous 3 classes. Is there
Consult one of your colleagues. Consult your colleagues. Some of the material is uploaded. Whatever is missed, consult with your colleagues. And all the information that we share, I try my best to send out messages. So students, the messages are all there in Schoology. Just look at those messages or consult your colleagues. All right?
All right.
But some of the lectures are already uploaded. All right?
All right, sir.
Cool. Take care.